In this video, I want to demonstrate the difference between sampling with replacement and sampling without replacement. And I'm going to use the game of Catan to help explain the difference between these two ideas. Now, just as a review, and I know I've talked about this a little bit in class, but Catan is a really fun board game that I've been playing with my family for a couple of years now. And a couple of interesting phenomenon came to the surface in playing this game in terms of randomness and in terms of sampling, this idea of sampling with replacement and sampling without replacement. Now, in this game, in this board game, Catan, the numbers you roll are actually pretty important to the game. You can see there are these hexagon pieces, and on the hexagons are little discs with numbers. And the way it works is when you roll a number, if you happen to have a settlement, now this little red house looking thing is called a settlement. If you happen to have a settlement, say that the number rolled is a 3, and you had a settlement here next to this, or at an intersection here with this hexagon, you would get a resource, you would get a sheep. Now, you can also probably see this 9 over here. So this settlement, or this is actually a city, but this city, if a 9 were rolled, this city would actually get 2 resources because it's a city and not a settlement. But again, I'm not really, the purpose of the video is not really to teach you how to play Catan, but just to illustrate that the numbers are important. So the interesting thing about the game is the first time we played this game, I played it with my 2 children and my wife, the 4 of us, and I realized as a mathematician, I realized that some of these numbers would come up more frequently than other numbers. And nobody else in my family realized that. And so I didn't say anything the first game, or actually the first couple of games. And I was having a lot of luck. And so eventually I gave my family a little lesson in probability distributions and helped them see that, for example, the 9 here is going to happen more frequently than the 3. And the reason is there are more ways to roll a 9 on a pair of dice than there are to roll a 3. There's only 2 ways to roll a 3. That's a 1 on one dice, or a 2 and a 2 on the other, or a 2 on the first dice and a 1 on the second dice. But there are more ways to roll a 9. So this idea of the probability or frequency distribution becomes important for this game. And then also, as long as I'm on the slide, you can see these little dots down below. And in fact, the dots tell you how many ways that number can be rolled. So there's 1 dot for the 12. It's only one way to roll a 12. That's a pair of 6s. There are 2 dots under the 3 and so forth. 4 dots under the 9. And so those dots tell you as a player how often you should expect to see the numbers come up. So we should see 4 times as many 9s as 12s, for example. Now, the first version of the game we played had these dice. And the dice are cool, I think, are really actually very good for probability modeling because they're different colors. We have a red die, and we have a yellow die. And so that distinguishes the 2 dice. And we can see that, for example, rolling a 3 on the red die and a 4 on the yellow die, that's a 7, would be a different roll than rolling a 4 on the red die and a 3 on the yellow die. So again, when we first started playing this game, we were playing with dice. We only had one version of the game, and it came with dice. So over time, we got so into the game that we started buying these, what do they call them? Expansion packs for the game. So you could play different versions of the game. And one of the expansions we purchased had these cards instead of the dice. They're called event cards. And so first of all, the cards, there are 36 cards in the event deck. And you'll notice, for example, these are the 7s. 1, 2, 3, 4, 5, 6 7s. 1 12. All right, is that a 12? I guess so. They're kind of in reverse order. think those are the 2s, 3s, 4s, 5s, 6s, 7s, 8s, and so forth. So there's one card that corresponds to 12, one card that corresponds to 1. So instead of the dice, we started playing the game with the cards. And the experience with playing the game with the cards was very different. And I'll confess, at the time, I hadn't really thought about it very deeply, but I was noticing that the game seemed a lot more predictable when we played with the cards. And then I thought about it and I realized that there's a dramatic difference between playing the game with the dice versus playing the game with the cards. So I want to bring this frequency plot up to start with. Now, whether you're playing with dice or whether you're playing with the event cards, the frequency distribution looks the same in the beginning. And so here we have, the number of sevens. There are 6 ways to roll a 7. And so again, in the deck of Catan event cards, there would be 6 sevens. And there's 2 ways to roll 11, 1 way to roll a 12. And so we could actually calculate all the probabilities based on this distribution. So for example, if we were interested in the probability of rolling a 12 on the pair of dice, it would be 1. There's 1 way to do it out of 36. And the same would be true from the deck. As long as you shuffled in between every card that's drawn. In other words, if you put the card that's drawn back into the deck, shuffle it, and then deal out a card on each turn, it would be the same as rolling the dice. But in the game, once you play a card, it goes away. And you don't get to play that card again unless you happen to go through the entire deck of 36 cards, and then you start over and shuffle the deck. And so, again, I started to get interested in this, and it's been kind of fun with the family because we've had these debates. My younger son is very lucky, it seems, and so he wins very often when we play with dice. And I tend to do better when we play with the deck of cards. So it's interesting. And strategically, when you begin the game, where you place your settlements and things initially can have a long-term effect on the game. So I wanted to take a minute and demonstrate to you how we could simulate rolling the dice on the calculator versus drawing cards from the deck. So I'm going to start off talking about the dice. And to keep everything just really simple, I'm going to model this for 36 rolls. So that would be like going through the deck one time. There are 36 cards on the deck. So if you played 36 turns using the deck versus 36 turns using the dice, we're going to see what the differences are in these probability distributions. So the first thing I'm going to do is set up the simulation. So we're going to use random integer for this. And notice I'm not worried about seeding the number generator here. That was in a previous lecture. We talked about that. But I do want to modify this. I'm going to do 36 rolls total. I actually learned something new about the calculator. It's funny, it didn't dawn on me when I originally started to do these examples, but you can actually do 36 rolls and add all 36 outcomes together in one step on the calculator. So in the past, I've been using the putting the results in 2 lists and adding the lists together, which also works. This is just a shortcut. And actually, I'm using a CE here, TI 84 Plus CE. I haven't tried this on the 83 or the regular 84 Plus, so I'm not sure it works for those calculators, but it's worth trying. So in any case, what we're going to do here is we're going to do 36 rolls on the red die. That's this first random int on the left. And then we're going to add that to the 36 rolls of the yellow die. And then the sums I'm going to store into L1. And again, I'm not going to ask you to replicate this simulation or anything like that. So I'm just doing this for illustrative purposes. Now I'm going to store that list into L1. I should have done that in one step as well, but that's okay. I'll come back and show you how to do that. So the window, I'm gonna use something on the calculator called a histogram. It's just a quick way to see frequency distributions. And again, I'm not necessarily trying to teach you how to do this in this video. What I'm mostly interested in doing is showing you what these distributions look like. So as I talk through this, or work through this, there we go. I'm going to, all right, so now I press graph. So this is what the frequency plot looks like, or the histogram, which I'm thinking of as a frequency distribution. And I can see the numbers on the histogram on the calculator by pressing trace. So this first bar would be all the twos that came up in the simulation. There were no twos. So we did 36 rolls of a pair of dice, fair rolls, fair dice, random rolls, and we got no twos. That's not too surprising. But there were 3 threes. Now we'd only expect 2 threes, but again, since we're sampling replacement on the dice, each of these numbers can happen way more frequently than you would expect them to. Now I see this really tall bar. That's the sevens. So normally, they're in the card deck, if we were playing with cards and not dice, there would only be 6 sevens in the deck. And that's all the sevens you would have. But here with the dice, notice we have 8 sevens. And, the sevens are a bummer, kind of, because there's this one piece called the robber that gets put on a number, and then that number stops producing resources, which is a bummer. And then the other thing can be a bummer about it is if you have too many cards in your hand, you have to sacrifice some of those. So there are some downsides to rolling sevens. So again, here, in this particular dice version of the game, there would have been 8 sevens, 2 more than you would expect. Now this bar over here, though, this is what really causes a difference in the experience of the game. In this particular simulation, there were 7 nines. Now again, we would only have 5 nines if we were playing with the card deck. That's all we could have. I'll come back and explain that more in a little bit. So we had way more nines here playing on the dice than we would expect. Oops, and I notice I'm not seeing one bar. So I actually need to adjust my window. I didn't notice that. 2 to 13 is what we need to do here in order to see all of the bars. So there's the last bar is 12. So we had no 2s, but there were 2 12s. Now, just to kind of give you a flavor for how much variability we can have in this distribution, I'm going to do a few more simulations. And the fun thing here on the TI is that we can do these pretty rapidly. Oh, I guess I did do a store into L1 here when I originally did this, so that's good. Now I'm going to press enter again. These are like 36 brand new rolls, so it's like we're starting over again in the game, and we're going to roll the dice 36 times. Well, again, this is the shape of distribution we expect to see, and this is what we end up with. Now this bar, the 3 bar, is pretty tall here. So we have 6 threes. We only expect 2 threes. So there were three times as many threes in this game. No 4s. So if you had chosen to put your pieces next to one of the 4 hexagons, you wouldn't have gotten any pieces. Although, if we were playing with the card deck, we would be guaranteed to see 3 of those 4s at some point in the game. And 9 sevens, way more, 2 more sevens than or actually 3 more sevens than we would expect. So you can see when you're playing with the dice, you have this way more variability in terms of what can happen. And luck plays a much greater role when you're playing with the dice. And again, we got 4 10s and we would only expect 3 10s. And I can go back and forth and do this simulation a few times just to kind of see how much variability that we can really have when we're playing with the actual dice. And notice this bar, this shape looks much more like what we would expect to see. But yet again, there's this 11s, way more 11s in this particular 36 rolls than we would expect. So again, It's 4 11s. That's twice as many as we would expect. I'll do one more here. And so again, roughly the same shape, but again, this bar is taller than we would expect and so forth, and probably this one too. So again, more variability when we're playing with the dice. I'm just wondering if I can get a really wacky one. Now this is wacky. Now, so I mean, if we were playing the game of Catan, and this happened to be our batch of 36 rolls for a game, this experience would be so much different than playing with the card deck, because what is that tallest bar right there? That's 9. There were 12 nines in that one game of 36 rolls. So what, a third of the rolls in that particular set were 9s? And again, we would only expect 4. So we've got 3 times as many 9s popping up in this game. Now, incidentally, when we're playing the game of craps in a casino, that's not such a bad thing. I mean, that's when the table really gets exciting. The batch of 36 rolls that has, only 4 7s and 12 9s. And people would be really excited over that. But in the game of Catan, and again, in the game of Catan, it might be a great thing if you happen to put your pieces next to the 9 or the 9s on the board. You're going to be getting all these resources that you wouldn't be getting if we were playing with the cards instead. So let me just transition a little bit and talk about the difference and what happens when you're playing Catan with the cards rather than the dice. So here, suppose, and again, I'm just using the calculator here to simulate drawing a random card. So we draw a random card off the deck, and it happens to be a 4. Now, in the frequency plot here, I put the 4 in as an X, or as a red X. So that would be gone now from the distribution. You wouldn't be able to get another 4. And then suppose the next roll was, or the next draw of the card was the 10 card. So again, that card would be taken out of the deck. It's played. And you would go to the next card, which is, I guess I didn't have the calculator to go with it here, but the next roll was a 9. So the 9 would be gone. So eventually, again, there's an element of randomness, because when the deck's well shuffled, these are random events of the cards coming off the deck. It's just that there are only 36 cards in the deck, so we know that each card is going to get played, and when it does get played, it does not go back in the deck. So again, the difference here is between sampling with replacement and sampling without replacement. And like I said, when you're playing the game with the card deck, you can count on there being a certain number of each of these in the game. Whereas if you're playing it with the dice, anything can happen. Now, there's one other thing I want to illustrate with this example. I want to illustrate this idea of the law of large numbers. And, one of the things that makes the dice experience with the game so much different than playing with the cards is the number of turns before the game's over. Now, I've been keeping track. I use 36 rolls here and 36 cards just to make that easily comparable. But it seems like the typical Catan game depends. I mean, there are different versions of the game, of course, like I mentioned, which some take longer than others. But usually there's somewhere between 40 and 60 rolls is what I'm noticing for a full game. So you usually go through a deck when we're playing with the deck rather than the dice. You go through the deck once and then through it almost twice, but not quite. So again, there is a little more randomness there, a little more of a not as perfect of a distribution when you shuffle the deck and start with a new deck again. But it's still nothing like rolling the dice. Now, if it took say 500 turns to play a game, we wouldn't see nearly as much difference between the experiences with the dice versus the cards. And to illustrate that, I want to go ahead and do another simulation. So let me clear this all out. I'm going to go back and I'm going to just change the 36 in here was the number of random integers we were asking for. And I'm going to make that 500 now. So that's like, this will be like rolling the dice 500 times. And we'll take a quick look at what that distribution is going to look like. And I can tell you right now, it's going to look a lot more like this every time. So let's see. It's going to take the calculator. That was pretty quick. So the calculator just got 1,000 random numbers, 500 on for the red die, 500 for the yellow die, added, and then I had the calculator add those together. I need to make a quick adjustment here in my y's. For a histogram, the height, the y coordinates are the counts. So if we're doing if we're doing 500 rolls, we need to increase this considerably. And I'm guessing at this maximum number here. I might have to change it. So you see that there's still variability in here, but not nearly as much. And it looks roughly the shape that we would expect to see. And again, sometimes we'll see that even when we have lower numbers of samples. I'm going to do the simulation a couple of times here just to see the differences. So much, again, more mound shape. There was a few more, what is that number there? There were a few more sixes than we would expect. But again, not nearly as, there's no bar that's sticking up here like in the previous example for 36 rolls. That would make things like really stand out in terms of the experience with the game. So you can see most of the time we're getting that basic shape of the distribution. I could call it the theoretical distribution. I'll do one more just to kind of. And if you want to, this is again fairly easy to do on your calculator. I mean, if you want to play around with this and kind of see for yourself. I use 500 here just because it doesn't overflow the calculator. We could crank this up actually to even more. 999, look at that. Again, looking very much more similar to this. Let me just go ahead and try the maximum number of cell. So the calculator limits us to 999 numbers per list. And again, the CE might have changed. That might have changed with the CE. Let's see if this works with this new version of the calculator. All right, and again, I'm gonna adjust this window because now I have nearly 1,000. I'm just again guessing at what Ymax should be here. So look at that, much more similar to this shape. I'll do a couple more simulations at 999 rolls of the dice. Just again to illustrate this, very much the same. So again, if we were playing a game, if it took say 1,000 rolls to play one complete game of Catan, it really wouldn't make a whole lot of difference whether you were playing with dice or whether you were playing with the cards. I'm actually, I know I'm dragging the video on a little bit, maybe because I'm actually enjoying myself here with these simulations. It's fun to look at this. Again, over and over again, I'm seeing the same basic distribution. And this is, again, what we call this the law of large numbers. What happens is these are the simulated probabilities. This one's a little bit off. You can see there's a heavier weighting of results on the left side than the right side. So that would be a little, the luck would have more of an effect in this particular set of game if we were playing it. And so what the law of large numbers says is the more times you repeat the simulation, the closer the relative frequencies will get to the actual theoretical relative frequencies. And what I mean by that is, notice there are 6 ways to roll a 7, or if, again, with the Catan card deck, there are 6 7s in the deck. So we would expect to see 7s 1/6 of the time. And similarly, There are, let's say, look at tens. There are 3 ways to roll a 10, or 3 tens in the Catan event deck. So we would expect to see a 10 happen 3 times out of 36, which is 1 time out of 12. So once every 12 rolls on average, we would expect to see a 10. And just for fun, let's see how many 10s did we get here. We got 70 10s. So let's see, what did I say? 1/12 of the time. So well, let's just do 999 divided by 12. And we would expect to see 83 10s. And what did we end up with? We ended up with 70 10s. So a little few less than we would expect. And then we would also expect to see the same number of 4s. And we're seeing something closer to what we would expect with the 4s. But again, 1,000 rolls isn't really a lot of rolls when we're talking about the law of large numbers. If we went up to 10,000 rolls or 100,000 rolls, be seeing very little deviation away from these expected relative frequencies. And again, the relative frequency is the fraction of the time we expect that event to happen. So the event roll a 7 happens 1/6 of the time. The event roll a 12 happens 1/36 of the time, because there's one way to roll a 12 out of 36 possibilities. So I hope this video helps clear up some of these ideas. Please be sure to message me if you have any questions. Have a great day.